Hey, welcome to Maths for Computing Week 2. So, there is something I forgot to teach back in week 1, which is point decimal values conversion with point binary values. So, let's say you have a number as 10.625. How do you convert this number to a binary value? Well, first things first, you have to make this number into a sum of two different formats. One, the whole number, plus its point version, the decimal version or something. So first off, you convert the 10 to a binary value. So do repeated division. You're gonna get 1010. So that is the 10. But what about the 0.625? Well, here's how you convert the number. So any point value, 0 point, is also 0 point in binary. Okay, right. So you're going to take a 0.625 and you're going to multiply it by 2. You're going to get a 1.25, right? So this number, this whole number, is the only number that you want to record. So this 1, you're going to put it over here. And you're going to subtract that 1 and you're going to take 0.25 over here. Again, multiplied by 2, you're going to get a 0.5. This is the number that we record. So we're going to put a 0 over here. We don't subtract any value if there is no ones. We take the 0.5 here, multiplied by 2. We're going to get a 1. So this one we record, and when we subtract 1, we get a 0. And any value times 0 is equal to 0. So we don't have to consider it. So this is 0.625 in binary format. So we add it 0.101. So 10.625 is equal to 101 in binary format. So this is one example. Let's try one more example, but because I want to show some very distinct feature of this conversion, because you don't want to do it with random numbers. Let's say you take a number 0.89 and you want to convert it to binary. Well, here is the issue. So 0.89 times 2 is 8, one more balance. So that's a 16, so 1.78. Good, you're gonna get a 1, subtract a 1, 78 times 2. Well, that makes a 6, balance 1.5, 1. 6 times 2, 1.12. 0.12 times 2, 0.24. Since there is no value, we don't have to record it. The thing is, what I wanted to prove was this can go on and on sometimes. And sometimes you may notice that there's a specific pattern. So something that you can mark with 2 dots like this. So if it's a 101, 101, you can mark it like that. So there is quite a bit of an issue when it comes to converting point decimal values to point binary values, right? So this can keep going on and on. So what I would like to recommend is, if it takes too much time, do not spend that much amount of time on that conversion, because you may lose time in your exams for other stuff. So anyways, delete that. Okay, so what did I learn on week 2? Well, this is the main things we're going to focus on. Mainly, we are going to focus on computer arithmetic, as in, we all know computers only have ones and zeros. So we will be learning to do arithmetic with these numbers, as in addition, subtraction, multiplication, and division. We'll also be learning the 7 deadly sins when it comes to multiplication and division. Then we will learn the general equation for complements, and I will also teach you an easy way to do complements along with it. Then finally we will learn logic gates. So before we learn anything else, let us first of all talk about computer arithmetic. So computer arithmetic is simply adding, subtracting, multiplying, or dividing ones and zeros. So if you add a 0 and a 0, you'll get a 0. If you add a 0 and a 1, you're going to get a 1. If you add a 1 and a 0, you are going to get a 1. If you add a 1 and a 1, you will get a 10. Now, the only time that you want to get a value carried over is another 1. So 1 plus 1 plus 1 is equal to 11. So let's take a random number, 10110, and add it with 1111. Remember, always write the bases. So 0 plus 1 is 1, 1 plus 1 is 10, 1 plus 1 plus 1 is 11, 1 plus 1 is 10, 1 plus 1 is 10. It's that simple, okay? So that is addition taken care of. What about subtraction? Well, when it comes to subtraction, it's a bit more nuanced. So how about I show you with an example? Let's take the number 110101, and I'm going to subtract 111 from this. So when you subtract 1 from 1, obviously you're going to get a 0, right? But you cannot subtract a 0 from a 1. So what you're going to do is you're going to borrow this 1 over here. So when you borrow a number, a binary number from here, the easiest way to see it is you're borrowing a 2, right? So when you borrow a number from one place to another, you're borrowing a 2, which actually in binary values is 10, right? So it's much more easier to see it like you're borrowing a 2 from here. So let me take another color. So this becomes a 0 and this becomes a 2. So 2 minus 1 is 1, right? But this is a 0. So, and you can't subtract a 1 from a 0. So what you do is you borrow this one here. This becomes a 2, right? So from this 2, you borrow a 1 here. So this becomes a 2 and this becomes a 1. So 2 minus 1 is a 1. This was a 2, but you borrowed from it, so this becomes a 1. This is a 0 and this is a 1. It's again as simple as that. All you have to know is when you borrow a value, it adds a 2 to the 0. So that's all you have to know. And when you borrow, if you borrow from a 2, you're subtracting a 1 and you're adding a 2 over here. That is how addition and subtraction work. So now we talked about addition and subtraction. Let's talk about multiplication of computer arithmetic and division of computer arithmetic. Before we talk about these two, we should talk about something which was taught to us, the 7 deadly sins. So the seven deadly sins is 0 to the power of 0, infinity to the power of 0, 0 to the power of infinity, 0 divided by 0. I do not remember the last three. Let me quickly check. Um, okay. 1 to the power of infinity, infinity divided by infinity, and infinity minus infinity. Now, apparently this is the right way of writing infinity. You should not close the loop. So there is that. Keep that in mind. I don't know how we're going to write it. So back to the subject. So let's say you have the number 11011 and you're multiplying it by 1 0. Again, it's just the same as normal multiplication. So here, as you can see, you're gonna make this all into zeros, and you're gonna make this into 11011. So if you multiply any number by 10, even in decimal values, you're gonna just simply add the zero at the end. Similarly, you can do that here. But what if it's not a zero and it was an 11, right? Or any of those values? Well, all you're doing is simply adding the value again. So 1 1, this becomes 1, 10, 11, 10, right? So this is how you multiply. But what about division? Division is exactly the same as regular old division. But what's the difference? Well, the difference is that you have to write the quotient and remainder of every time you divide. For instance, let's say you divide the number 111011 by 111. Well, as you can see, we can divide this by this, right? So you know, 1 1 giving a 0. You take this 0 down, is there anything? No, there is not. You take this 1 down, is there anything? There is not. You take this one more down, is there anything? No. So the quotient is 1000, but the remainder is 11. You have to write this every single time. So this is for, so every single time you divide a number, you have to write its quotient. When it comes to computer arithmetic, you must write its quotient and you must also write its remainder. This is very, very important. Now we will talk about something a bit more interesting, which is complements. So first off, we must understand why people use complements. Complements is used especially for finding negative values. So if we have a binary system, the binary's first complement is like a negative value, and the binary's second complement is like it is used as like a guarantee, so there won't be any mistakes that happen. Similarly, every single other system has a complement value. So the general equation for the complements are, let's say we have R, which is representing the base. We have N, that represents number of digits, and we have, sorry, N, which represents the number which you're trying to complement. N dash is its, well, it is usually its complement, and N double dash is its other complement. Why is this? Well, I think it's best if you realize for yourself. So N dash, its R minus 1 complement, is equal to the base times the number of digits minus 1 minus the number. Okay, so essentially what this does is it creates like this max value, right? Now for binary, the max value is always 1, so any type of any number that you have, you're just going to add a 1 1 1 1 1, right? Because that is the base, right? Now let's say you have the binary value. Binary is a number consists of 0 to 9, right? So the max of binary will always be the number of 9999. That is the max. For octal, the max number is 7, so it will create a 7 7 ish for how many numbers that there are, for how many number of digits there are. For octal, sorry, for hexadecimal, it will be F or 15, right? So when you subtract your number from something like the max of these digits, right, you will get its minus 1 complement, the base minus 1 its complement. And when you add 1 to any of this, you're not adding a 1, you're not adding a 9 to the 9, you're adding 1 to every, regardless of the base. You're simply only going to add a 1, then you will get the base's complement, right? I don't think I made a lot of sense, so let me show what I mean with a small example. Let's say you have a number that is, we'll go simple, we'll start binary. You have 110, you want its, so the base is 2, right? So you're gonna get 2 complements, is in r minus 1, which is the first complement, and r complement, which is the second complement. So to get the first complement, what we do is we subtract this from its max value, right? So 1 minus 1 is 0, 1 minus 1 is 0, 1 minus 1 is 0, 1 minus 0 is 1, 0, 0. This is its first complement. To get its second complement, we simply add the 1, so that is 1 0 0 1. Now let us talk about the binary number. Let's take the binary number 289. To find its ninth complement, see, it's 10 minus 1 makes a 9. We subtract this from 9999. So we can get a 0 1 7. This is its ninth complement. To get its 10th complement, we add a 1. That's going to make it a 7 1 1. This is the 10th complement of the binary number 289. Now, what about octal? Well, the principle remains the same. What is the max value of octal? Well, it's a 7. So let's say you have a number 673. Now you have to remember, if you see an octal number that has any number greater than 7, let's say 9, it is not an octal number, because as you know, octal only has 0 to 7. It only has 8 digits, right? It only has 8 characters. So beware to have that in mind. Okay, so if you ever see something with a base 8 but you see a number that is greater than 7, let's say an 8 or a 9, then it is unfortunately a wrong statement. So be very wary of that in your exam paper. So here, to find its 7th complement, see, this is 8, we have to find 7th complement. We subtract it from its max values. 7 7 7, so 7 minus 3 is 4, this is 0, and that's 1. This is the 7th complement. You add 1, you're going to get a 105, right? This is its 8th complement. What if you subtract something like this, say 670, or let's say you subtract 600, so you're going to get a 177, right? What will happen if you add 1 to this? Well, 7 will pass on and it will become a 0. this will also become a 0, and this will become pass over here, and this will become 200. So essentially what you must realize is that you should not limit yourself to 0 to 9. If it's 0 to 7, then 7 is its final digit, and if you get an 8, it will pass on that. If you get a 9, it will pass on that. So if I, using octal base 8, I add a 7 and a 7, right? I'm going to get a 20. This is for base 8, right? Because 7 and 7 is the maximum, so I'm going to add a 0 here. I'm going to put 2 over there, right? So it's very important that you don't confuse yourself over this. Finally, let's have one more answer. Let's take A6, 7, and this is a hexadecimal number. Well, to find its 15th complement, see, 16 minus 1 is 15. We subtract it all from F. Now F's value is 15. A's value is 10. So 15 minus 10 is 5. F minus 6, well, that's going to make a 9. 15 minus 6 is 9. What about 15 minus 7? That is going to make an 8. Right? So you add 1 to it, you're going to get a 599. Right? What if you subtract a value, let's say A00? You're going to get a 500. You won't get a 500, you'll get a 5FF. What if you add a 1 to this to get its 16th complement? Well, you will get a 600. Do you understand? So this is the basic idea behind complementary numbers, right? And finally, what we learned was something which we all know and we are very familiar with: logic gates. So this is an AND gate, this is an OR gate, this is a NOT gate, then there is a NAND gate, NOR gate, and a very unique one, an XAND gate. So the truth table for an XAND gate is as follows. So let's say there are two inputs, A and B. You get an output F. So this is the truth table. You'll only get a 1 when one of the two inputs is 1 and another is 0. If both of them are 0, you'll get a 0, and if both of them are 1, you'll get a 0. Well, how do you draw this? Well, here's how. So you're gonna have one like this, and you're gonna have one like this. So, and let's say this is A, let's say this is B, this is an AND gate, this is also an AND gate, this is an OR gate. So let's say A and B are both 1. Well, ones will become zeros, and we know AND gates don't like zeros. But let's say A is 0, right, and B is 1. Well, if A is 0, well, then this won't allow it to pass, but this will, because the 0 will turn into 1. B will be 1, 1 and 1, and gate like 1. So it will let it go through, and it will give us this output. So that's a special gate, an XAND gate, and as far as I know, there is no XOR gate. I don't know if it exists. So that is all for week 2, maths for computing. Another thing that we have learned in the lab, so this week's lab, we learned about a few things in GNOME, especially the way we can utilize logic operations, logic and relative operations. So Right now we are taking it slowly. So right now I'm using the command window so that whenever I click enter, I can get an answer, right? Because if you remember last time we spoke, an editor is a script, right? These are scripts. You can run them to get the answer, but you had to specifically run them. But instead of using editor, we can use the command window here, because I'm just giving you an example of how things work. So relative operations, when it comes to relative operations, to see whether two numbers are equal, we use double equal, right? So is 9 equal to 9? Yes, the answer is 1, which is true in Boolean, right? Let's say if 9 is equal to 8, the answer is 0, right? Let's say 9 is not equal to 7. True, 9 is not equal to 7. That's why 9 is a 9. Now you might wonder, why on earth will we use this? We obviously know that 9 is equal to 9 and not 8 or 7. Well, we can use this when it comes to comparing variables. For instance, let's say a is equal to 2 and b is equal to 3. Well, now we can check whether a is less than b. It is true. So as you know, there are few well-known relative comparisons. So there is the equal, is it equal to, is it not equal to, is it greater than, is it less than, is it greater than or equal to, is it less than or equal to, so on and so forth, right? So that is the relational operators. Now we will also know about logical operators. So let's say we change a is equal to, how about we say 20, right? And we also have b is equal to 25. So we can say that if a is less than 30, and so if you want an and, that is the symbol that you must use, double ampersand, b is greater than 20, so and so should happen, right? So right now the statement is true. That is the condition. The condition is true. So similarly, we can use this for O. This is the, I'm pressing shift and slash backslash, that is right above my enter key. This is I have a laptop that has a smaller keyboard, hence this. You may have to find it if you're using a bigger PC. And finally we have something of a not. Not is especially just, an exclamation point, right? So that is all the things that we have learned this week. Sure, we can create, these are good for conditions that we can use later on. If so and so, we can, if so and so is true, we can apply a logic or a program or something like that. Anyways, that's all we have learned. That's it for week 2. Have a great day.